Thank you, TJ. Yes, I'm Dr. Lauren Behrman, and it's my job today, in fact, it's my honor today to be able to talk to you in a very broad sense about remote sensing of the oceans. Um, and so you're going to, as Shubha has very aptly told you, there are going to be a number of modules that take you through everything I'm going to talk about today in much more detail. But this is just hopefully going to give you a nice introduction to remote sensing of the oceans. And I think one of the first things one should do in a talk like this is justify why. Why do we care about remote sensing when we talk about marine ecosystem monitoring? And that's because really, genuinely, this is one of the best tools that we have for observing our Earth. We have data from long time series studies in around Hawaii and Bermuda. These are hot and bats. And even in the gyres that we consider to be relatively the equivalent of ocean deserts, we have seen annual cycles and interannual variability of phytoplankton, of microscopic floating plants in these remote ocean gyres. So we see that there is a diversity and patterns within even the least productive waters on Earth. However, unfortunately, even if we had bats and hot all over the world, we would still be collecting point measurements across our oceans. And it is only with remote sensing that we can elevate that data to be able to get overviews and synoptic coverage for entire oceans. And when it comes to ecosystem monitoring, we have so many amazing tools at our disposal. And I would say some of the key things that we can monitor from space and that we use for ecosystem monitoring are things like sea surface height, ocean color, and sea surface temperature. And we are able to observe these variables from low Earth orbit using a number of sensors. And you can spend an entire career, devote your entire academic and research life to any one of these three topics. But I would say the most interesting thing happens when you combine them. For example, if you look at ocean color along with sea surface temperature, you can understand and observe things like harmful algal blooms, the dynamics of plumes along coastal edges, coral bleaching, and of course, human health. And human health is such an important theme in this series. It takes up a module that is going to be covered by Grinson, Shubha, Gemma, and Milton. So this is the intersect where we're able to use different data sets to tell us really important things. Between ocean color and sea surface height, we start to understand things like sea ice dynamics. We're able to track and observe underwater volcanic eruptions and internal waves. And of course, something very important is an application for transport of things that are good, so phytoplankton blooms, and things that we should be worried about, like pollutants. At the intersect of sea surface height and sea surface temperature, we're able to look at eddies, anomalies. We're able to start to contribute to forecasting and maritime safety and observe storm dynamics as well. And of course, I've talked about the intersect between two at a time, but the magic really happens when we look at the center and we look at the overlap of all three. Because when we do that, we're able to see things like essential climate variables. We're able to become really involved in disaster response. El Nino and La Nina, the states and the impacts. These are things we can observe and track using the intersect of these three. Climate model assimilation, insurance risks, which underpin the aspects really of our lived experiences, marine spatial planning, and anomaly development, which is very important. And so having now told you that we're able to look at ecosystem monitoring using these three types of variables, you are perhaps not going to be surprised to know that there are lots of different sensors out there that are going to be able to help you to do that. And I think one of the most interesting things is that switch that happens when you start to integrate remote sensing into your research, which is you first arrive and you don't know what's out there. And after a period of time, you know what's out there and you start to go, but there's so much out there, what do I actually use? But ultimately, as different or as unique as each of the sensors are, they are underpinned by similar physics. And that is that all of them utilize sections of the electromagnetic spectrum, and each region of the electromagnetic spectrum will tell us different things. So different satellites utilize different parts of the electromagnetic spectrum, and from that we can derive different variables to measure. Um, Passive and active sensors are used for ocean monitoring, so we're going to cover this in a bit more detail. Passive sensors are your optical sensors. They rely on sunlight coming through the Earth's atmosphere, striking the Earth's surface, interacting in some way with the target that you're interested in, bouncing back through the atmosphere and striking the target on your Earth observation, on your instruments on a satellite. It's quite extraordinary. Active sensors are different in that they don't rely on sunlight. They can see through cloud. They send out a signal in the electromagnetic range, and then they receive the backscatter from a surface interaction. But both of these can be used for ocean monitoring. Within optics, different bands that are collected can be used for different processes. So for example, for ocean color, you might be most interested in 2 or 3 bands, but actually it's information collected all of the way into the shortwave infrared that's going to be necessary for you to do an atmospheric correction. So all of these data are important. And if I've misled you, I apologize. I've made it sound like this is a perfect solution to doing the job of ecosystem monitoring of the oceans. But it is important for me to start and end with this message. There have to be trade-offs because there is no one perfect tool for one perfect job. And the trade-offs tend to be around temporal and spatial scales. And the British have a lovely term, I really like this, the rule of thumb, or in general, you can't have everything. And I think that's true for just about all types of science, but remote sensing is the same. And I've divided this up into time requirements, but you can split this the other way around. If you need data collected multiple times in a day or at very specific times, the sensors that are going to be available to you for the job are going to be sensors aboard drones or airplanes. They collect very high spatial resolution over small areas, and they do so on the day that you specify. You can fly that drone yourself and collect the data yourself on the day that you need to do it. Or commercial satellites, which collect very high spatial resolution data over specific areas, and you have some control over at what period of time that data are collected. If, however, you need data every single day, you're on a totally different system here because you're going to be using data at low spatial resolution from satellite sensors that have revisit times of 1 to 2 days. So very different things with just a day's difference. If you need data every 2 to 5 days, so we're looking at maybe once a week to every couple of weeks, I think this is the sweet spot personally for me, for my work. You get to access high spatial resolution data with moderate spatial coverage, but you get the data every few days. And of course, if you only want to get an overview of what's happening on monthly, seasonal, or annual scales, then you have a better selection, but you tend to be looking at data at level 3 or level 4. And I'll explain a little bit more about what that means. So I've tried to sort of visualize what I've just talked about and illustrate it in this way. And hopefully it takes away the confusion and doesn't add to it. But if you are, as I said, looking for data collected multiple times a day or on a specific day, you're looking somewhere over here, and I hope you can see my mouse. You're looking at your drones and commercial satellites, which collect data at very high spatial resolution on your specific days. But actually, geostationary satellites might also be able to give you data every day or multiple times a day, but the spatial scale is different. The ocean color satellites that I'm going to talk about today give you data on daily scales at resolutions of about 300 meters to 1 to 4 kilometers. Then if you need data multiple times a week or multiple times a month, you get these satellites at higher spatial resolutions and temporal resolutions of about a week. And then at the process scale, if you want data once a month, once a season, or annually, you start to look at these level 3, level 4 composites. This will make sense to you by the end of the talk. And I'm going to talk to you a little bit more about these satellites within this realm. And I'm going to focus specifically on ocean color. Why ocean color? More specifically, what is ocean color? It is literally what it says. It is the color of water. When sunlight hits the ocean, some is reflected back, but most of it penetrates the surface and interacts with water molecules and whatever else is in the water. Now, if you've ever been lucky enough to go scuba diving, one trick that's really cool is you take down something red, and within a very short distance below the surface of the water, it turns brown. Red wavelengths of light are absorbed really efficiently by water, and as we move out of the visible into near-infrared wavelengths of light, that becomes even more true. Near-infrared light hardly ever penetrates below the skin of the water. However, blue light and even green light can penetrate much further at these shorter energetic wavelengths, and so we're able to derive a lot of information between the green, the blue, and the red. The reason we care so much about this is because phytoplankton are the base of the marine food web. And that is a simplification, but ultimately, if you think of phytoplankton as the grass of the ocean, you'd know that absolutely all life in the sea is somehow linked to these tiny microscopic unicellular organisms that we can't even see with our eyes. But they are responsible for through the process of photosynthesis, they take up carbon dioxide. They're responsible for removing more atmospheric CO2, and they convert that into organic matter, which then gets eaten and sinks. So this is very simplistic, but don't worry about it. You're going to hear a lot more about this from Anna, who's going to talk about the role of phytoplankton in ocean color. And I wanted to share this with you. This is a really beautiful animation that was put together by NASA, showing you the color of the ocean and of the land. And I like that these are linked because you really should think about phytoplankton as something that is not so separate from what is happening on land, from plants. We have in the ocean, we have deserts, we have jungles, we have parts of the ocean that are rapidly changing. And these changes reflect multiple physical and physiological changes in the ocean itself. In many regions, we're seeing decreases in productivity due to changes in nutrient supplies, which are driven by temperature changes. So what we see there is a response driven by changes in more physical drivers. In polar regions, the reduction in sea ice is changing productivity as more sunlight reaches the ocean surface. In the mid to high latitudes, there's complex interactions between stratification and light limitation and nutrient limitation, and increased growth rates because of the warmer temperatures. We're seeing changes in structures and communities all over the world. There is changes happening in every single part of the world, and we can see this through the base of the marine food web because of these microscopic drifting plants that when they are in their niche, when they receive enough sunlight and nutrients, they bloom in such capacities that we can see the way that they change the color of blue water to closer to the green and the red. And we can see that to such an extent that we can measure it from space. And Anna, of course, is going to be talking about this more. And so is Thomas Jackson, Heather Bowman, Margaret, and Dio. This is part of follow-on modules because it's such an important recurring theme. But this is really, you don't actually have to see the ocean to understand ocean color. If you've ever seen a lake or a river, I'm sure you'll understand what I'm talking about when I talk about muddy waters or waters that have been changed in some way by something inside of it. So river estuaries, for example, here's a nice example. They're brown because of resuspended sediment. Here's an example of a bloom in the North Sea, and that blue water has been moved closer to the green. In the Atlantic Ocean on the top right-hand side, that is water that has no phytoplankton in it, whereas in the Florida red tide, that is water that has perhaps too much phytoplankton in it. And all of this is the color of the ocean is now changed by what is in it. And of course, because nothing is simple, we have to understand the fact that we like to measure water closer to land, and that's where things get really complicated. So complex waters, because of the influence of land, because of runoff and CDOM and resuspended sediment, it then becomes increasingly tricky to distinguish what is changing the color of the water and in what proportions. Is it phytoplankton or is it sediment? And Son is going to talk more about this during the course as well. But ultimately, we're looking for these microscopic unicellular drifting plants as the sentinel species. They're telling us everything that we need to know about the ocean, and they themselves just alone are beautiful. I'm going to start off with the remote sensing data that you can look at yourself in terms of ocean color as well from NASA, because I think at the end of the day, when we think about ocean color, the first organization we think about is NASA. So we're going to start with them because they deserve this place at the beginning, certainly. And we're going to talk about perhaps their flagship sensor, certainly at the moment, which is MODIS. These radiometers sit aboard two sensors, the Terra and Aqua satellites, and they give us extraordinary coverage every 2 days with data acquired in 36 bands at 300-meter spatial resolution, which means MODIS has been giving us data for over 20 years, which is incredible. I know for a fact there are people on this course that are younger than these satellites, but we can go back and see what was happening in the summer of 2002, thanks to MODIS, and then in the spring of 2003, and then we can compare how things look now to how they looked 20 years ago. But actually, 20 years is maybe nothing, because we can go back further than that thanks to CWIFs and the Coastal Zone Color Scanner. These sensors collected data from 1997 and 1986, and CWIFs collected data at 1.1 kilometer resolution, spatial resolution, in 8 bands on daily scales. So we can go back to 1998 to see what the oceans looked like compared to now. But actually, we can go back further than that. And that's thanks to USGS and NASA, a joint program called Landsat. And these were launched in 1970. So the Landsat data that we can use was launched in 1979. And I'm very old, but that's older than me. So there has been data collected by Landsat since before I was born, every 16 days, initially in 4 spectral bands, but now at 311 with the new generation of Landsats at 30-meter spatial resolution. And I hope that you stopped there and thought, 30-meter spatial resolution, because before this I was talking about 300 meters, 1.1 kilometers. How has this been such a step change? Well, that's because Landsat is primarily a terrestrial mission. But this is going to be a recurring theme in this talk as well. Just because something was built for land doesn't mean it can't tell you something about water. And this is one of my favorite examples of an underwater volcanic eruption as observed by Landsat, showing you new land developing and changing fundamentally the color of the water around it. And I really love this example. 30-meter spatial resolution data every 16 days. We managed to get such great gaps in the cloud. And this has persisted to this day with new land, which has changed the color of the water around it because of the amount of sediment that was resuspended, but also the nutrients and the change to stratification in the area. And that leads me to the next generation of satellites through the Copernicus program. Now, what I didn't mention before, or if I did, I would like to reiterate it. All of the data I'm going to talk about in this talk and all of the data I've mentioned so far are freely available to any of you. You can use it for anything you want. And this is true for the Copernicus program as well. The data are available to you for free. And Ben Loveday is going to talk a little bit more about how you can access these data as well. Within Copernicus, though, we have 2 agencies, and this is important about data access. EUMETSAT takes care of generally the marine component, whereas ESA, the European Space Agency, takes care of the terrestrial component. And you might be wondering why there is a split of responsibility there. And that is because of how ambitious the Copernicus program is. It is responsible for so many things that it would be that it does make sense to have organizations take responsibility for different aspects. And I'm only going to be talking about this tiny component of what is going on within the European Commission's Copernicus program. And I apologize in advance. This is a horrible slide, but it is a really important one. So please bear with me. The point of this slide is to show you the sort of umbrella of the European Commission's Copernicus program. And it's important because at some stage you are going to want to access the data. And I would just like you to remember the slide when you inevitably go to ESA for marine data or EUMETSAT for terrestrial data and you go, oh, wait, I remember that horrible slide. I go to EUMETSAT for marine data and I go to ESA for terrestrial data or marine data collected by Sentinel-1 or 2. Because even though ESA collects terrestrial data from terrestrial satellites, like I showed you with Landsat, there are marine data everywhere. You just need to know how to find it. But we're going to start with Sentinel-3. This is our beautiful blue ocean satellite. It's a dedicated marine mission, and it carries 3 sensors, which already makes it extraordinary. And predominantly going to talk about Algae because we're interested in ocean color. And ocean color data here are collected at 300-meter spatial resolution from 21 bands on a 1 to 2 revisit time, so almost a daily basis. Sentinel-3A has been collecting data for us since 2016, so we have data going back to 2016, and that data doubled up in 2018. So the Sentinels always act as a constellation of two, and they do that in order to cover themselves in case something goes wrong with one of the satellites, but also because of cloud gaps. Algae is a passive sensor. It cannot see through cloud. It can't measure data at night. And cloud gaps are a big problem with optical sensors, but having two going in conjunction helps you to fill in those gaps. And it also means you have better coverage. Now, the mission's primary objectives, of course, there are different data delivered for terrestrial applications, but the primary objective of this Blue Sentinel is to deliver a sea surface height, sea surface temperature, and chlorophyll. And this is what it looks like. These are where the three sensors are situated. We have the SLSTR, which is the sea and land surface temperature radiometer, to collect our sea surface temperature and land surface data, but we're obviously going to focus on the sea surface temperature. We have ALCHI, which is our chlorophyll or ocean color sensor, and the ocean and land color instrument, and then SRAL, which is our long track surface radiometer, SAR altimeter, sorry. And EUMETSAT is responsible for operating these satellites and for the data access, data processing and dissemination. So this is where you access your ALCHI, your SLSTR, and your SRAL data. And the applications are really only as small as your imagination. But I've put up the ones that are relevant to the modules that you're going to be following on from this talk, which is, for example, human health, like tracking waterborne diseases. By taking the temperature of the skin of the sea, we're able to start to assess and look for sea surface temperature anomalies in conjunction with chlorophyll A and pH to assess risk of cholera outbreaks along coastlines. And this is really important because as sea surface temperature increases, so too does the risk of these Vibrio infections under warming conditions. And you can measure this data at the same time as your ocean color data to give you chlorophyll A, which is really important. The long track radiometer altimeter data, sorry, that is collected is an active sensor. So this can see through cloud, which means it can see through storms, and it allows you to get measurements of sea surface height anomalies and wave heights. So you can start to be prepared for disasters, and you can start to be involved in maritime safety by using this long track altimeter data. I just want to say thanks to Ben and Haley who provided a lot of these slides. But this is the active sensor SRAL aboard Sentinel-3. And then, of course, our focus for ocean color is ALCHI. And this is just such a beautiful example of what ALCHI can do. It's really showing off in this, and you might not realize why. But I just want to say, if you look at the color bar, ALCHI in a single scene is able to resolve the difference between water that contains practically no phytoplankton at 0.1 milligrams per cubic meter, all of the way to this incredible bloom at 100 milligrams per cubic meter. And it is able to do that because of its incredible sensitivity and signal to noise ratio. So it really just, this image just really continues to blow my mind. Every time I look at it, I'm really in awe of what ALCHI can achieve. And it measures a lot, as was with all of the optical ocean color sensors I've talked about so far, to one optical depth. And that is, of course, dependent on what's in the water to begin with. Here's a beautiful animation of ALCHI at work. It's collecting data over the Earth at 300-meter resolution and 1 kilometer reduced granules. It is collecting data in 21 spectral bands, so in the RGB and the visible, into the shortwave infrared. And as you can see, it's going over the UK now, and it's collecting data right now over this beautiful bloom in the Bay of Biscay. And now it's moving over land. You can see it's not collecting data through the cloud. And because it is such a democratic sensor, it is now also provisioning ocean color data over the land as well. And yet again, if I've managed to make it sound like this is a one solution for all problems, then I apologize, I've misled you, because there are significant challenges to collecting data on ocean color. with optical sensors. And the first one is that Earth is really cloudy. And I believe I'm right in saying that one of the most common responses to when people go into space for the first time, astronauts go into space for the first time, and they have this unbelievable opportunity to look back at our Earth, one of the first things they always say is, I can't believe how cloudy it is. Earth is cloudy, and that's a problem if you can't see through cloud. I'm going to give you just a few seconds to look at this and figure out what that is. What do you think that could be? I'll give you a clue. That is what the world looks like to just one of the sentinels on a daily basis. Two challenges here. The first one is cloud, and the second is swath gaps. But when you combine Sentinel-3A and B over the space of a single day, you cover those swath gaps, but you're left with significant cloud gaps. There's lots we can do to fix this. So today is Wednesday, is that right? Today is Wednesday. If I want to know what the global oceans look like without such a big impact from cloud and with absolutely no impact from swath gaps, I can convert data that was collected on Monday, I can merge data that was collected on Monday and Tuesday to give me a composite. And now we have no swath gaps, but again, lots of cloud. But I can continue to merge and merge and merge data from today, data from tomorrow, until I get weekly composites, monthly composites, seasonal composites. The only thing limiting me is what I'm trying to measure. And if I'm lucky and the things I'm looking for are out in the bigger ocean and they're changing on very slow scales, then I can make composites of up to a week or a month. But this is not often the case, especially if you're working in the coastal zone where things change multiple times a day. But that's not our only challenge. We have solutions to it, but it's not our only challenge. The second challenge is that the Earth has seasons and latitudes. Now, this picture is amazing. Regina Falkenberg made a pinhole camera and she put it in an observatory near her university, and then she proceeded to forget about it completely for 8 years. And when it was found, it had collected 8 years worth of data of the sun moving across the hemispheres. And so what we can see is what the sunlight path looks like in winter and in summer, because it is different. I'm going to demonstrate this in the best way I know how. Here is the Earth with an atmosphere floating in space. It is on an axis, which I've obviously greatly sort of exaggerated for illustrative purposes. Here's me, I'm waving. I've also grossly exaggerated me for illustrative purposes. And if I am standing straight and I'm imagining a line from me to the center of the Earth and I look straight up, that line goes straight through me, and I look straight up, I'm looking at the zenith. And in summer, even in the UK, I can anticipate the sun to be directly above me in summer at midday. Beautiful sunlight coming through the atmosphere. But that's not always the case, because in winter, as we saw from Regina's photo, the sun is not above my head at midday. It comes in at an angle to strike me in the eye as I'm cycling home. And that has a few implications. The first is that it has more atmosphere to travel through. And the second is that it creates the solar zenith angle. Now, if you're trying to see the bottom of a pond at night, you would shine the torch from the top to illustrate the bottom. If you shine it at an oblique angle, you're very unlikely to get the kind of penetration through the water that you want. And this is a very simple concept, but it's the same thing. You have more atmosphere to deal with, but you also have an oblique angle of light penetration to deal with, which means in winter, the data you're collecting is not, it should be flagged. And if you're able to account for this, then that's fine. But you need to be aware of it, because if you're looking at data over the space of a year, you might think you're seeing something, but it is in fact an artifact because of the way the light is penetrating or not well penetrating the water. And it's a significant amount of the Earth that is affected by this solar zenith angle. So anywhere sort of north of Portugal, during winter months, you have to account for this high solar zenith angle. And if you're anywhere sort of south of Cape Town, that is true for the Southern Hemisphere winter as well. So this is a challenge if you're trying to get data collected on annual scales. Finally, I've mentioned the atmosphere, but it is in fact its own challenge all on its own. The Earth having an atmosphere, and I've sort of said this to you before, for optical sensors that are passive, light from the sun sort of comes through the atmosphere, it interacts with the Earth's surface, it bounces back, and it's about 2% of the original light that makes it back to the satellite. But we really do have to account from the contributions of Rayleigh scattering and other interactions and contributions from the atmosphere, because what we want is the signal called the water leaving radiance. So we do have to do atmospheric corrections. Now, if you're very lucky, you'll never have to do an atmospheric correction in your life, because data can be processed for you. And it depends on the level of the data that you interact with. Now, you'll never interact with level 0 data. But if you download and process level 1 data, it's gridded, it's beautifully formatted, but it will not have an atmospheric correction applied. That is something that you will have to do yourself. Now, this does vary slightly between different data providers, but in general, if you are using level 2 data, you are using data that has an atmospheric correction applied. At level 3, we're talking about data that has been merged in some way. So for example, the OCCCI, which TJ and I'm sure Shubha will talk about during their talks, is the Ocean Color Climate Change Initiative Composites, which merges data in order to get the longest possible timescale. So the sensors I've spoken about from NASA and from ESA are part of these climate change initiative, the Ocean Color Composites, in order to get the longest possible time series. And you'll hear more about that later. And then at level 4, we get gap-filled product data that has had model data included. And a very good example of this is primary productivity. And Bob Bruin is going to tell you more about that in his lecture. And of course, Ben Loveday is going to tell you a lot more about the data access at these different levels from different places as well. The nice thing about getting level 2 data from EUMETSAT for ocean color is that you also, not only do you have data that have been atmospherically corrected, but they also compose the products for you. So you get 2 chlorophyll products, the neural net and the OC4ME, products like total suspended materials, Gelbstoff and PAR, which you can use or not use depending on your application. At level 3, this is just you can obviously tell this is one of my favorites because I use the spinning globe in all of my talks multiple times. Thomas Jackson created it from the version 5 Ocean Color Climate Change Initiative product. And this is that merged product for using different sensors. And it is available to you for free as a daily, a 5-day or 8-day composite or a monthly composite. And that goes back to 1997 using a lot of the instruments that I've talked about in this talk. And again, this slide, and I'm sorry, but this is just to remind you because I promise it's important, and you will think back to the slide and you will say, okay, I remember and I thank you, because we're going to now move from ecosystem monitoring to marine monitoring. And that's because we're now using terrestrial satellites to do a marine job. And the first satellite I'm going to talk about for that is Sentinel-1. This is an awesome satellite. It collects radar data. So this is the first active satellite sensor that we're going to be talking about in detail. It collects data at 10 meter spatial resolution. Again, we've now moved from 300 meter spatial resolution to 10, and that's because we're talking about primarily terrestrial sensors. It was launched, the first one was launched in 2014, and this is the perfect example of why having 2 at a time is amazing. Sentinel-1B regrettably stopped collecting data in 2021. We only have 1 radar satellite that we can use the data freely now under the Copernicus program. And that had big implications for data coverage, but at least we still have 1. They carry C-band synthetic aperture radar instruments, what Sentinel-1A does, and this is that active sensor I was telling you about. So not only can it collect data in most weather and through cloud, it can collect data at night. Again, mostly a terrestrial focused mission. And for those of us used to getting the in-water properties, you need to forget that now. We're talking about only surface backscatter. The other thing, if you're used to data collected by sensors I've mentioned before, is that Sentinel-1 is not switched on all the time. And I apologize if this makes you feel a little car sick. If it does, please rather focus on this little panel at the bottom with the yellow square. Sentinel-1A this is its path, and it is collecting data based on where it is switched on. And you can see it is switched on and switched off over different parts of the world. and it is collecting data in the marine environment, but mostly only because that marine environment happens to be next to land, very much a terrestrial sensor. But well worth the efforts of getting used to its unique ways of collecting data, specifically for things like vessel detection, because it doesn't matter if you're doing something naughty at night, we can still see you from SAR. Oil spill detection is a very useful application of SAR because of the way oil sits on the surface of the water and reduces the capillary waves. We're able to detect it as dark patches on an otherwise quite bright background. And because SAR data, particularly in VV polarization, is very sensitive to the ruffling of the surface of the water by wind, we can also extract wave and wind information from the SAR surface roughness. In areas of the world where clouds are a problem, specifically the poles, this is sometimes one of the only ways you can collect any data throughout the year because of cloud and because of the solar zenith angle. It is also very important for inland and coastal flood monitoring. And more recently, it has been shown to be very good at picking up seaweed invasions. So this is Barbados, and all of these bright objects against the gray background. I've tried to enhance it a little bit so it's easier to see. I hope you can see it. Almost looks like a stars against a dark background, but that is in fact an invasion of sargassum seaweed that during 2018 was unprecedented and caused a state of emergency for Barbados. So here's a really nice example of where we're used to these sensors for marine monitoring, but actually this is more in the realm of ecosystem monitoring too. And because of the high resolution and because it is ostensibly a terrestrial satellite, it is of course not just valuable to us for the oceans, but aquatic systems in general. Here's another invasive plant, this time a freshwater plant called water hyacinth that has invaded the Saigon River, and we can see it moving towards Ho Chi Minh City in this thick rope of invasive plant in the Saigon River using Sentinel data, Sentinel in VV polarization in this example. That brings us to Sentinel-2. Again, not a marine mission, but has marine applications. You can derive ocean color from this instrument. It is another passive optical sensor. And I'm going to give you an example of some of the ways you can visualize what Sentinel-2 can do. And this is one of my favorite things to do, is to look at the world through Sentinel-2 eyes. And what it has done here, it has taken data collected in the visible bands of light in the red, the green, and the blue. It has put them together and recreated what we would have seen had we been flying over the Shandong province of China ourselves. But what is the first thing you notice? It's a little bit disappointing because it's hazy. Can't really see a lot, but don't worry. We're going to do an atmospheric correction together. Are you ready? There we go. Don't worry. It has now been atmospherically corrected at the push of a button. If only it were that easy, right? So here you can start to see a lot more detail. It is absolutely spectacular. Look at the beautiful swirls of sediment in the water. This is obviously quite complex waters. There's a lot going on, lots of contributions from sediment. But can you start to see, I hope you can start to follow my mouth, and you can start to see there's something going on there, isn't there? There's something in the water that looks to be regular shaped all over the place, actually. And one of the nice things about Sentinel-2 is it collects data in the near infrared. And remember, I told you right in the beginning, near infrared light is really effectively absorbed by water. It doesn't penetrate past the skin. So water will look black, and anything that isn't water is going to be bright in comparison. So why don't we take things from the visible into the invisible through Sentinel-2 eyes? Wow. Suddenly you can start to see that on or at the surface of the water, there is a lot going on. These two boats, in fact, are not just moving towards the shore, they're moving in a channel. And what they're moving between are seaweed algae farms, macroalgae farms, where we have ropes, individual ropes that have been strung across that are growing macroalgae for food production. And they're absolutely everywhere in this image. But if we just rely on data in the RGB, that is really hard to see. And this is where the different bands start to really come into their own. I really love that. So the data goes back to 2015. Again, we have two sentinels acting as a constellation. It is a passive sensor that can't see through cloud. The optical data are actually collected at different spatial resolutions, but we don't need to worry about that right now. Suffice to say that we have Sentinel-2A and B acting together, collecting high resolution data, predominantly over land. And it is an excellent sensor for what it was designed to do. Its priorities are around land monitoring, but it has few bands. So we talked about Olchi, we said it had 21 bands. Sentinel-2's got 12. And it doesn't have an excellent signal to noise ratio for that sensitivity that we managed to get out of Olchi. But it does have some strengths, mainly based on its high spatial resolution. We can observe surface blooms. In fact, our background today is a cyanobacteria bloom that I think was observed by Sentinel-2 at high spatial resolution. We can monitor water quality. We can look at aquaculture farms like I just showed you in the Shandong province of China. Whatever you see in radar, it's really good to do sanity checks or validate with Sentinel-2 wherever possible. Very valuable for marine spatial planning and for detecting floating debris. And again, because it is ostensibly terrestrial, you don't just have to do marine applications like ocean color in the ocean. You can also extract phytoplankton and chlorophyll in inland waters, thanks to this higher resolution. I've got one more really cool image to show you. This is another example of how Sentinel-2 sees the world. Here we're going to do another atmospheric correction and go. There we go. Start to see things with much more clarity. There's some beautiful interactions between some fresh water and some ocean, but we're not going to focus on that too much. I'm going to ask you to look in this little block over here. And again, with how we saw in China, there's perhaps not a lot of anything to see. We're going to move like we did into the near infrared, and suddenly there's lots to see. There's a lot going on. And this is at the 10-meter resolution scale. So while we can't see exactly what's going on, we know something's going on. And this is perhaps where it's a good time to introduce the role of commercial satellites, because I certainly talked about them at the beginning, and I'm going to mention them again now. So this is what data can look like at better than 1 meter resolution in the same band in the near infrared from commercial sensors. And you might be thinking to me, Lauren, why did you bother telling me about all of these other sensors, 300-meter resolution? I want to see the world like this with perfect clarity. Well, I'm sorry, but that's not the way it works. The very important slide I said at the beginning, everything has a trade-off. And never is that more true than when it comes to this kind of high resolution data. So I know it's tempting, trust me, I do. When you want to look at things at finer spatial scales, there is a temptation to move to very high resolution data, especially if you've got a lot of budget for commercial data. And here is an example that Haley put together showing the difference between Sentinel-3 Ultra, the Sentinel-2 multispectral instrument, and satellite data from a commercial satellite called PlanetScope at 3.5-meter resolution. And you might think, that's it, I'm done. I'm only using PlanetScope data from this point on. Be careful because of that trade-off. And this is very important when it comes to the spatial and spectral, particularly the spectral resolutions. So in the same space on the electromagnetic spectrum, where Sentinel-2 collects data in 9 bands, Sentinel-3 has managed to cram in 21. And that is very, very important if you want to resolve things with more clarity and sensitivity. Whereas that commercial sensor I just showed you, I mean, it looked great, but you're lucky to get data in 3 or 4 bands. And more worryingly, for scientific applications, the signal to noise ratio, as you go down in spatial resolution, becomes worse. And maybe that's not so relevant for your application, and that's okay. But for things like ocean color, particularly in complex waters, where you get something like this, you have to know what's inside. And in order to tease apart, to unmix what is causing the change in your ocean color from blue to green to red, it's important to know what is CDOM, what is chlorophyll, and what is sediment, because you're trying to measure chlorophyll as the base of the marine food web to tell you many other things. And so having more bands at higher spatial sensitivity, sorry, higher spectral sensitivity becomes very, very important. And again, I'm not saying commercial data isn't for you. I'm just saying that it has to be the right application for the tool to work well. There is a sweet spot for everything, but it is really important to remember for whatever you plan to do with your remote sensing data, resolution, resolution, and sensitivity. Those are the key concepts to remember. So I've drawn it back around to talk about the limitations and the trade-offs. But please don't let that put you off. There is nothing better for marine ecosystem monitoring than remote sensing. It is the very best tool that we have at our disposal for gathering overviews, for synoptic measurements at long time scales and at good spatial scales. Yes, trade-offs often need to be made, but that is very much dependent on your application and your workflow. All sensors, and in fact, I don't know any instrument for any scientific application that doesn't have strengths and weaknesses. And as long as you're aware of those and the challenges that impact data collection and accuracy, I think you're good to go. If you are interested in distinguishing climate change trends from long-term climate cycles, then merged sensor records become really important. And this is really the strength of the Ocean Color Climate Change Initiative, where we are getting data that is uninterrupted all of the way back to as early as we can get it. And as I said, TJ and Shuba, I'm sure will talk more about that. Despite the imperfections, there really is no better tool for giving us the insight and understanding that we need of marine processes on everything from site-specific scales and dynamics to the global trends. And I really, really encourage you to go all of the way through this course, of course, but for you to take what you've learned today and ensure that you attend the last module in order to be able to take what you learned today and find out how to access the data and process it using a number of tools that will suit your application and your workflow from Anna, Broer, Jeremy, Dave, and Gail. So really, please make sure that you don't miss those lectures in July. And they also include machine learning, which is a very important tool when you start to work with very large data sets. And I would like to end by saying thank you to you for your attention. I hope that was informative. I'd like to extend special thanks to Haley and Ben because they provided a lot of the slides, particularly on Sentinel-3, to Thomas, Stefan, and others at PML for contributing slides as well, and particularly to Shuba and Trevor because it was one of these lectures that I attended at the beginning of my career that turned me into a remote sensing scientist. As TJ said, I discovered remote sensing during my PhD and never looked back. And it was in a lecture just like this one with Shuba and Trevor at the helm that changed my career for the better. So thank you to them as well.